Hey Algebra 2 friends, we are looking at logarithms and logarithmic functions. So today we're going to talk about what a logarithm is, and it's such a big word. I am hoping that you guys took the opportunity to check out the videos that I asked you to watch. And if I haven't asked you to watch, because that happens sometimes, please go on YouTube, check out some videos, history of logarithms. It'll be helpful. We'll talk a little bit about what they are, but the history is somewhat fascinating and interesting and really deep. So let's talk about what we need to know for our class. So a logarithm really relates to a relationship between an exponential function. Simply put, a logarithm is an exponent. But let's see how we can write that down. So you know that 3 to the second power is equal to 9. And here we would say this is like an exponential relationship. I can rewrite this exponential relationship as a logarithm where now the exponent is the answer. And so that would be like this: log base 3, because that's the base of the exponential relationship, of 9 is equal to 2. Basically, we're saying, okay, if I'm dealing with base 3, if I'm taking 3 and I'm raising it to a power, what power am I going to raise it to in order to get 9? So I literally, because I don't use logarithms in my everyday life, I literally write this down sometimes. If I'm working with a student, tutoring, or teaching a class or something like that, and I want to keep the logarithmic relationship in my mind, I will write this down, maybe even color code it so I can keep in mind what a logarithm is and how it relates to an exponential expression. So a logarithm basically refers to this expression whose answer is an exponent. So in a sense, a logarithm is an exponent, right? The whole thing basically gives us an exponent. So what's a logarithmic function? Glad you asked. It's when you have a function such that you have the log of some number, let's say b, and you are trying to figure out, and it's a little bit different, like this would be your x value and this would be your y value. So notice the exponent is actually the y value, the log base b is a part of the expression, and x would be all of the values that you are taking the log of given that particular base. Now that sounds a little bit weird, but we're going to talk about it a little bit more. A logarithmic equation is going to be an equation that involves a logarithm, and it could look like this, where we're trying to figure out what n is based on the fact that we're dealing with a base 2. We know that 2 to some power 1/2 is equal to n, and we would figure out what that value is. And a logarithmic inequality would be a logarithmic expression that's not really an equation, but an inequality, or I shouldn't say expression. A logarithmic relationship that's not an equation, it's an inequality. So it could look like this, where we're trying to figure out what the x value would be to satisfy this relationship. Let's get started with some examples. So as I mentioned before, I literally do this. I know that log base 3 of 9 is equal to 2 because 3 to the second power equals 9. So I put that there just to help me out when I rewrite these logarithmic expressions or logarithmic equations in terms of exponential expressions. So this is 8 to the power of 0 is equal to 1. Over here, let's try it again. We take the base, which is 2, we raise it to the exponential power, and we set it equal to the thing that we're taking the log of, log base 2 of 116. And so we've done that. Here in example 2, we have exponential equations that we're going to change to logarithmic form. Again, I place my handy dandy relationship here, and I use that all the time. And so what I'm going to write here is that I'm dealing with log base 10 of the number 1000, that's equal to 3 because 10 to the third power is 1000. Same thing here. I'm going to write log base 9 of 3 is equal to 1/2 because indeed 9 to the 1/2 power is equal to 3. So we're going to use the examples that we saw in 1 and 2 in the situation of changing a log to an exponential expression in order to help me out here while we think about evaluating this particular logarithmic expression. So going back to what we said, we know that information is there. I realize that this means 2 to some power, that's what I'm looking for, is going to be equal to 64. Well, you know what? This looks like the problems we solved in the last section where we had to make sure that both sides had the same base. So we've got 2 to the x, and if you know anything about 64, you know that we can write that as 2 to the 6th power. And so, since we have an equivalent relationship, we can then imply or say that we know x is equal to 6. Continuing on with this way of looking at these problems, I'm going to really look at this, and now I'm going to think about the problem without rewriting it, but you can if you want to. This problem is saying 6 to some power equals 6 to the 8th. 6 to some power equals 6 to the 8th. If we do write it down, which I said we weren't, but whatever. If we write it down, we can see clearly that x is equal to 8. Let's try this one. So here we have 3 to the power of log base 3 of 4x minus 1. My goodness, what's happening here? Let's first just take a look at the exponent here. All right? This exponent refers to an exponent. What? It's too much to think about. This is so crazy, I'm going to zoom in. So I'm zooming in to the wrong problem. Let me go back to the correct one. So if I zoom in here and I look at log base 3 of 4x, just this yellow part, what this is saying is this number refers to 3, let's say, to some power x, and I'm going to highlight in yellow to show you that this yellow number is this yellow number. So what this problem is saying, 3 to the x power is equal to 4x minus 1. That's what this is referring to. So this thing is this x here, because remember, the answer to a logarithmic problem is an exponent to that base. So this is saying, I want to know what the x is when, oh, I shouldn't use x, I should use like some other variable because it can't be the same x. My bad, Chavalitos. Let's say y. I want to know what y is such that when I raise 3 to the y power, I get 4x minus 1. I want to know what that is. But the cool thing here, I hope you've seen it, is that if this thing is that thing, then 3 to the y, or 3 to this thing, has to just be 4x minus 1. I say pause it and think about it. The answer is 4x minus 1. Pause and think. Hopefully example 4, that last one, wasn't too hard. Let's look at example 5. We're going to solve a logarithmic equation. So here we have log base 4 of n is equal to 5 halves. And so what we know is that 4 to the 5 halves power has to equal n. Again, keeping this relationship in mind, or the relationship with a logarithm to its exponential equivalent equation, would help us out here. So 4 to the 5 halves power is equal to that. Now, what is 4 to the 5 halves power? Glad you asked. Basically, it's 4 to the 1 half, then raised to the 5th power. And so 4 to the 1 half is 2, and 2 to the 5th power is 32. So here we're looking at a logarithmic inequality. And so if we solve this equation or this inequality, we need to also check our solutions. And there's some specific reasons for that. The fact of the matter is the domain of the logarithmic function, and that's something we should talk about. So first things first, what we're dealing with here is b. That's the same b that we had when we were dealing with our exponential equation or our exponential function. Remember, y equals a times b to the x, where b had this restriction placed on it such that b had to be greater than 1, or b had to be some positive number between 0 and 1. And so we're going to take that into consideration as we consider what are the values that x can be. So if I have a basic number here, like in this situation, so some fraction, positive fraction, or some positive number greater than 1, what can x be? What are the values that x would be allowed to be? What's the domain? And if you think about it, you realize that we can't raise b to some power so that it becomes some x that's negative, right? Think about that. If I have some positive number, there's no power I can raise it to in order to make it negative. Remember, a negative exponent only makes a number smaller, like a reciprocal. So x cannot be any old number. X, in fact, replaces y. Let me look at a graph really quickly. So if we take a look at this Desmos graph, we are familiar with it from the lesson, talking about it whenever we talked about exponential functions. But if we graph, notice the same base, 2 and 2 here, if we graph the logarithmic function, we see that it has a particular relationship with the exponential function. And if you were thinking about it and you remember we talked about this, they're just inverses. They're inverses of one another. That's why we use one to get the other. And so, what I would like you to observe is that the domain for the blue function or the exponential function and the range for the exponential function flip flops with the domain and range of the logarithmic function. So now the x values that we can have here that make sense will be from 0, not including, all the way out to positive infinity. Whereas the y values are going to be like the x values, which would be all reals. I even get switched up. That's why I was like, what am I saying? But do you see what I'm talking about? Pause it here if you need to and think about it. This is deep stuff. So here is what this expression gives us. It tells me, having this expression, it tells me that, all right, x, we already know from our last conversation about the graph, x has to be greater than 0, okay? Because we know that that's part of the limits on x. However, this is going to give me kind of an upper bound. What this tells me is that x has to also be less than 5 to the second power. And we get that from just rewriting this as the related exponential inequality. So x is less than 5 to the second power tells me that the answer to this is all x, such that x is somewhere between 0 and 25. Or of course we can do interval notation and say that x is a part of this set from 0 to 25. Similar to the exponential situation, if I have log base something of something is equal to the same base of something else, right? If I have this situation, this implies that the two values here have to be equal. Let's think about it really quickly. Remember, this is an exponent. This refers to an exponent such that when I raise 5 to it, I get this number. But the fact that these are equal means when I raise 5 to that same exponent, I get this number. Therefore, these two numbers must be equal. All right, I know that was a bit of a mouthful. So now that we've got p squared minus 2 equaling p, we can solve this. I'll bring the p over to the other side, recognizing that we are probably dealing with a quadratic equation. And I think I should not have plus that 2. That should be a minus sign. And so now hopefully we can factor it. If not, we will be pulling out the quadratic formula. When I multiply, I know that I can do plus 1 and a minus 2. And I think I'm good to go. I'm going to factor each of these, set each of these factors equal to 0, and I get that p is equal to -1 or p is equal to 2. We've got to check our solution though. How do we check it? We plug it right back in. If I put a -1 here, -1 squared is 1. 1 minus 2 is a -1. So this is log base 5 of -1 on this side. We're going to think about that in a second. And if I put a -1 here, I get log base 1 of -5. So I get the same thing, but the question is, does it make sense? Can I raise 5 to a power such that I get -1? And after thinking about 0 or -0 or whatever's running through your mind, you'll remember we just talked about this. We cannot raise it to a power such that we get a -1. Such that we can get a -1. Therefore, this does not make sense. So the next value is to plug in the 2. And so we have log base 5 of 2 squared minus 2, which is 2. And does that equal to the same thing, log base 5, 2? Yes, that's fine. But the question is, does it make sense? Is there some power that I can raise 5 to in order to get to? That was too many 2's, but you get what I'm saying. And the answer is yes. There is. Even though it's not like a nice number that we know about, there definitely is a number I can raise 5 to in order to get 2. That makes sense. It might be a decimal, but we can handle it. All right, let's pick up the last example in the next video.